The invisible engine, decoding algorithm complexity in modern computing. In the intricate world of algorithms, where efficiency can make or break performance, understanding algorithm complexity is not merely beneficial, it's essential. This concept forms the backbone of how we evaluate and optimize code across industries ranging from finance to artificial intelligence. At its core, algorithm complexity measures how resources, primarily time and space, are consumed as input size grows. By mastering these principles, developers gain the power to create scalable solutions that thrive even under extreme data loads. Foundations of time complexity analysis. Time complexity quantifies the amount of time an algorithm takes relative to the input size. It helps us predict scalability by focusing on worst-case scenarios rather than average cases. This analysis often uses big O notation, which abstracts away constants and lower-order terms to reveal dominant growth patterns. For example, O, n superscript 2, indicates quadratic growth while O, log n, suggests logarithmic progression. Big O notation describes upper bounds of runtime without considering implementation specifics. Asymptotic behavior focuses on trends as input approaches infinity rather than exact values at small sizes. Understanding these fundamentals allows developers to compare different approaches objectively before implementing any solution. It also reveals why certain algorithms become impractical beyond specific thresholds. An O2 algorithm may work fine for n equals 10 but becomes unusable when n reaches 20. Space complexity, the often overlooked dimension. While many developers focus solely on execution speed, space complexity examines memory requirements, an equally critical factor in system design. Algorithms might have optimal time complexity yet consume excessive memory, leading to swapping issues or even crashes in production environments. Memory constraints are particularly crucial in embedded systems and mobile applications. For instance, a recursive Fibonacci implementation using O(n) stack space will fail dramatically for large inputs compared to an iterative version requiring only O(1) additional memory. Evaluating both dimensions ensures balanced optimization strategies that consider hardware limitations alongside theoretical performance gains. Dominant terms and asymptotic notations. Beyond basic definitions, grasping asymptotic notations unlocks deeper insights into algorithm behavior. These mathematical tools provide precise language for comparing implementations. Three primary notations define boundaries. Big O represents upper limits, omega denotes lower bounds, and theta signifies tight bounds where functions grow at similar rates. Consider sorting algorithms. Merge sort has theta, n log n, performance, whereas quicksort typically exhibits O, n superscript 2, worst case despite better average performance. Mastery of these symbols enables clear communication between engineers and facilitates informed decision-making during architectural reviews. Analyzing common algorithms through complexity lenses lets examine classic examples to see how theory translates to practice. Linear search demonstrates O(n) time complexity while binary search achieves O log n. Sorting algorithms offer rich ground for study. Bubble sort runs in O(n superscript 2. Insertion sort shows similar characteristics, while heap sort maintains consistent O(n log n performance. Graph traversal techniques vary significantly too. Breadth-first search operates in O(v plus e), while Dijkstra's algorithm requires O(e log v), with priority queues. These differences highlight why choosing the right algorithm depends heavily on problem constraints and expected input sizes. The role of constants in practical implementations. Though Big O ignores constant factors, real-world performance sometimes hinges on them. A O(n) algorithm with high constants could outperform a theoretically superior O(n log n) approach for small datasets. Cache locality, instruction pipelining, and branch prediction all influence actual runtimes independent of pure complexity classifications. Profiling tools help identify bottlenecks where theoretical guarantees don't align with empirical results, ensuring practical optimizations match analytical expectations. Recognizing this duality prevents over-reliance on abstract metrics alone while still maintaining awareness of fundamental scaling properties. Amortized analysis. Beyond worst-case scenarios, some operations exhibit variable costs depending on state. Amortized analysis provides a way to analyze average cost over sequences of operations rather than single events. Data structures like dynamic arrays demonstrate this well. The occasional expensive resize operation gets distributed evenly across many cheaper insertions. Using amortization arguments, we can show that inserting elements into a dynamically resizing array has an average cost of O(1) per insertion despite some O(n) individual steps. This technique proves invaluable for analyzing complex data structures where worst-case scenarios rarely occur in practice. Complexity trade-offs in real-world applications. Realistic engineering involves making deliberate trade-offs between competing objectives. Sometimes faster processing demands higher memory usage or increased pre-processing time. Approximate nearest neighbor searches sacrifice precision for dramatic speed improvements, demonstrating the value of probabilistic methods in big data contexts. Machine learning models often prioritize training speed over model accuracy, reflecting strategic choices based on deployment requirements. Each choice reflects careful consideration of domain-specific constraints shaping the final implementation architecture. Measuring performance. Tools and techniques. Empirical validation complements theoretical analysis through benchmarking frameworks. Profilers help pinpoint hotspots while stress tests expose edge cases. Tools like Valgrind assist with memory profiling, revealing leaks or inefficient allocations that impact overall performance. Timing measurements must account for external variables such as CPU load and disk I/O to ensure accurate comparisons between implementations. Reproducible testing environments guarantee reliable results that reflect true algorithmic behaviors rather than transient conditions. Emerging trends in algorithm optimization. Advances in parallel computing introduce new paradigms for evaluating algorithm efficiency. Traditional complexity models need adaptation for multi-core architectures. GPGPU acceleration transforms brute force problems into feasible solutions by leveraging massive parallelism inherent in modern graphics cards. Quantum computing presents radical shifts in computational complexity classes, potentially solving currently intractable problems within polynomial time. Staying current with these developments equips practitioners to anticipate future challenges and opportunities in algorithm design. Education strategies for mastering algorithm complexity. Effective learning requires structured exposure to foundational concepts combined with hands-on experimentation. Textbooks remain vital for building strong theoretical foundations. Coding platforms enable interactive exploration through instant feedback mechanisms that reinforce conceptual understanding via practical application. Collaborative projects foster deeper comprehension by exposing learners to diverse perspectives and alternative solution approaches. Regular practice with varied problem sets ensures mastery through repetition and pattern recognition development. Conclusion. Algorithm complexity serves as the compass guiding developers through the vast landscape of possible solutions. Understanding its nuances empowers teams to build efficient, maintainable software systems. By combining rigorous analysis with empirical verification, professionals can navigate trade-offs wisely and deliver optimized solutions tailored to specific needs and constraints.